All right, we're going to talk about cratering, not only as a scientific subject, but also as an example of the problems we have at making it science advance, particularly if a given theory has been around for a long time and is entrenched. The case here, cratering, people always thought they understood why there are holes in the ground, roundish holes in the ground on Earth, even easily observable on the moon and on other planets. But the cause of these was in some dispute for a long time. It took some good scientific work and a brave attitude to overcome prior prejudices about what really causes these holes in the ground. We're going to talk about that and use cratering as an example or a model for observing the scientific process and things that impede it. That's me. You see my email address there. This is a presentation I gave at the Little Thompson Observatory in Berthoud, Colorado in 2003, but all the results are still pertinent. So, our challenge in this talk is to explore this recent example, namely cratering, as an example of the scientific process and explore some specific questions. Why is it so hard to understand something that should be nearly obvious? And we're going to have some examples throughout here, but our primary focus is on cratering. If there are many cases of obvious explanation that have been missed, we have to ask ourselves as scientists, what are we missing today? What could we be doing better to use our common sense to throw away antiquated or wrong-headed ideas that are impeding our progress? So this is a fact I got from my friend Bruce Bohor, a retired geologist of prominence. Prior to 1960, professional geologists doubted that craters on our planet came from impacts from outer space objects such as comet nuclei or big rocks. Here we have a nice quote from Thomas Jefferson. Some people told him they had witnessed a meteorite, and you see his quote, "I would prefer to believe that two Yankee professors would lie rather than stones could fall from heaven." Unexpected source led to solving this problem, and we now know all the objects in the solar system have been bombarded. Earth has only a few observable major craters because of wind erosion, water erosion, geologic activity, and so forth. But we'll talk about that. So, craters. Here's Meteor Crater. I apologize for this picture. It's easy to find a good picture. I don't know why I chose this. This one is terrible. I mixed metric and English units. There's also a flaw, but you get the idea. Over a kilometer in diameter in northern Arizona, pretty roundish, if observed from above, and pretty deep, 570 feet. And we now think that an iron meteorite about 50 meters, up to 50 meters in diameter, hit this. There's a reference here to the idea of complexity. We'll talk about that. It's a little premature, but this hole in the ground probably resulted from a piece of iron 30 to 50 meters in diameter, and actually the Barringer family that owns this and has developed a visitor center and so forth. The original Barringer went looking for the iron. He figured this would be a better than digging iron ore out of the ground. You just go get a big piece of iron that's bound to be at the bottom of this hole. Well, the iron got scattered all over the neighborhood, so his idea for a get-rich-quick scheme didn't work out so well. An artist's representation of what, oh, and that's a video, forgot about that. So blast with a mushroom-shaped cloud, and we end up with this, this hole in the ground. So the crater, when it was first seen, those first visitors found approximately 15 tons of meteoritic iron scattered over the neighborhood. And this hole in the ground had been known for hundreds of years, but this is the first example we have of a crater that size being caused by something falling from the sky. And as I say, the early geological theories included these that are mentioned here: steam explosion. People knew about meteorites, but in spite of that, people thought it was a steam explosion or some other cause that has since disappeared, even though there's no volcanic rock in the area. Now, meteor craters out here, I guess it's this one, but there are meteor craters all over the planet, different sizes. And another clue, by the way, is about the source is, you see here's the ring of fire that extends across the Pacific, and down here lots of volcanic activity there, almost no craters. So, and they're randomly distributed. Of course, can't find them if they're in the ocean, unless it's right on the edge of the ocean, and there's the famous one in the Yucatan Peninsula. We'll probably talk about that as we go on. Here's observed cratering, the Shoemaker-Levy meteor breaking up and striking Pluto. Or this is, I guess, an animation, but you can go online and see the actual impacts of these pieces of the meteor, or the nucleus of the comet, striking Pluto, striking Jupiter. The moon is covered with craters, but Earth has been hit even more because of its larger gravity. And like I said, surface processes like these, erosion, infilling, volcanism, tectonic activity, have hidden many of them. Unless they're pretty young, they might be invisible. We have 160 craters that are known, and they're in geologically stable regions, so that's why they're still there. They haven't been subducted into the ocean or that sort of thing. So you saw the word complex earlier. There's a diameter at which craters become complex, and it depends on the gravity associated with the planet, and we'll see a picture of a complex crater in a second. So complexity in cratering on Earth depends on a size of the incoming object. If it's 2 to 4 kilometers in diameter, and depending on what it's made of, you can get a complex crater that has sort of a dimple in the middle. And it only takes 15 to 20, it requires 15 to 20 kilometers for that same kind of phenomenon to occur on the moon. So here's a simple crater. It's just a nice hole in the ground. And you see, this is the shape you see at Meteor Crater, Arizona. I've been there a number of times, and it's a pretty impressive thing. Here's what you get if the hole is 3 to 4 kilometers in diameter. You get this central bump, this dimple, or reverse dimple, little bump survives in the middle. So I think I said the wrong thing here. It's not the incoming object that's this diameter. That would be devastating. It's the hole in the ground that has this size, and that's the transition for simple to complex. And here's some cartoons that show us the size of a object coming in, producing a simple crater, and then if it's bigger, you get this either a simple bump in the middle or a complex bump in the middle. So, a pretty interesting crater I've been to is the Rice crater. It's in Germany, right near Munich. And once again, my friend Bruce Bohor advised me. My wife and I were going on a trip. He said to Germany. He said, "Oh, if you're going to anywhere near Munich, you should go to the Rice crater." Now, a little hard to see here, but these white things are clouds. This is an aerial photo, and that the group of clouds goes all the way around, and they show the perimeter of the crater. That's, I think, about 20 kilometers across. So summertime heat rising near the edge of the crater, you get these little puffy clouds that kind of are nice for identifying the location. And it's now thought that the object that created this was rocky and a diameter of a mile. Billion tons of rock hit the ground not that long ago. I think about 5 million years ago. It was going 10 miles per second. So millions of megatons of kinetic energy were invested to make this hole in the ground. And pieces of stone that were here were found far away, 35 miles. If you go to, and it shows, erosion of the hillside around has filled it in, but it was about 3 miles deep when it was first formed. If you go to the Munich area, go to the town of Nördlingen. I'll show you that in a second. There's a nice little museum there that describes this event. The town is approximately here. I think it's about that big on this scale. And there's also a companion crater nearby showing that the object that came in was torn apart by Earth's gravity. Tidal forces broke it, so there were actually at least 2 impacts, probably more, but the smaller impacts have been eroded away and cannot be found. So here's the Rice crater. This is in German. So Rice crater near the town of Nördlingen, which is somewhere in the crater here. And this is a geological map of what went on. Actually, there is some English there, but it's obscured by this picture. Anyway, sort of a circular hole in the ground. And there it is in profile. You can see here, Rice crater tomography. Some interesting stone was produced in the impact. I hear that geology students from the universities around the area are taken to this church, which is built out of this transformed stone that does not occur in nature very often. And they're given a little quiz about what is this stone. Well, it turns out this whole area was limestone. The blast incinerated the limestone and mixed it with other materials, and when the debris rained down and finally cooled, you get these blocks of material with little droplets of obsidian in them, little glass beads. So, and a lot of the town stonework is made out of those. Here's the town of Nördlingen. So don't confuse this with the crater. The town is a medieval town with a stone wall, and it's circular. The crater is nearly circular. And it's a beautiful little town. It's worth going to. It doesn't have much touristy stuff, which is kind of good. There's the church in the middle. Right outside the gate is a McDonald's. So you can plan to get something to eat there. So Eugene Shoemaker, whose name is going to be prominent in this lecture, was he and his colleague Chow were the first in the early, like 1960, maybe 59, 60. They analyzed this geologic structure and concluded that this is a result of an impact. And because Shoemaker had a great reputation, people were finally forced to confront this idea that cratering is the result of impacts. Prior geological studies had associated this hole with volcanism. Shoemaker faced a lot of criticism for publishing a paper claiming this was the result of a cratering event. But he had the right experience to know that this was the right path to follow, and we'll talk about that. Here's another little video of an incoming meteorite breaking up, in this case because of heating. I've had the good opportunity to see something called a bolide. Oh yeah, you can see the pieces here. A bolide in northern New Mexico one time, right around sunset, we witnessed an incoming meteorite that blew up as it passed over our head. That was pretty interesting. Oh, and this one, yeah, I forgot. This one, piece of stone hit a car. Did some pretty serious damage there. So here's a complex crater. It looks like a pustule or something from an infection. This one is a result of a volcano. There's several prominent structures like this on Mars, and this is one of those, Olympus Mons. This is huge, 3 times the size of the height of Mauna Loa on Hawaii, which is over 13,000 feet high. And the base of this one could fit all the Hawaiian Islands, would fit in this area. This is a crater, and this is a complex crater. It has the central dimple, 2 miles wide. Some other structure here. This is on the moon, and has the structure we showed earlier. This is a complex crater. I didn't put the size on here, but it's pretty big. But you see the others, the smaller ones, do not have that central structure. Here's the crater I mentioned in Chicxulub in the Yucatan. This is possibly the result of the impact that killed the dinosaurs. This is submerged, so it took some time to find this guy, but it's big. This is reference to the Lunar and Planetary Institute. So in the 1950s, Earth scientists considered cratering by impacts unrealistic and improbable, and astronomers had seen cratering on planets and the moon, other planets and the moon, and geologists weren't looking up, they were looking down, so there was conflict, and there were issues about the energy levels required to make holes in the ground. As I said, moon has been known since Galileo to be covered with craters, but they were attributed to volcanic process. And geoscientists typically in the early 50s refused acceptance of impact. Hager published a big paper about the Barringer meteoritic crater in Arizona, claiming it was a sinkhole. The interesting thing is, if you go look at old copies of National Geographic magazine, back in like 1915, they had an issue that included an article on Meteor Crater, and it was called Meteor Crater, which means that the author of the article and the editors at the magazine both accepted the idea that the crater was made by a meteor. Nonetheless, professional geologists refused to believe this, and that was as late as 1953. Oh, and then Hager tried to explain away the iron chunks that were around the crater site as being from a different event. So, and you have textbooks take a while to catch up, and the myth of flying saucers is mentioned in the same sentence as meteor impact. So this was considered heresy, even in the 60s. So here's the issue. The energy of the incoming object, if there was such a thing, is half mv squared. We've all seen that in our physics class. So what kind of energy do we get? A car going 60 miles an hour, 100 kilometers per hour, can do a lot of damage in a small space. Meteor velocities that we measure are measured in kilometers per second, not kilometers per hour. So the incoming objects that are observed have these enormous velocities, and that gets squared in the calculation of energy. So the energy in an incoming object is, compared to a car, it's going 40,000 times faster, and you get to square that. So there's 9 million times more energy in an incoming meteorite of the same mass as a car. And we're talking now about energy levels consistent with nuclear weapons. So, and here's a kind of a rule of thumb. The energy is released in the time it takes the meteoroid to cross itself. So, something going 11 kilometers per second, even if it's a kilometer in diameter, it takes 1,000th of a second for that event to happen. Or, sorry, an 11th of a second for that to happen. So all the energy comes out in a fantastically short amount of time. Yeah, 1/10 of a second. Now, one of the big impediments to understanding cratering was that scientists made the observation that there are no elliptical craters. The craters we see on the moon and the planets that like Mars are the holes in the ground are circular. And the argument was incoming objects would come in at different angles. Very few would come vertically and produce a round hole. Others would come in at an angle and produce an elliptical crater, and yet none were found. So the presumption was that cratering from the sky was impossible. And this gets to this issue about how your thinking is colored by an assumption that elliptical craters would be the result. So I've already said this, non-vertical impacts would create elliptical cratering, and nobody was seeing elliptical craters like that. They were seeing this. So a little aside here, if you go to the little museum in Nördlingen, and you'll find a little experiment you can do. It's a plexiglass box with sand in it and a pellet gun, and you get to choose the angle at which you fire the pellet into the sand. And there's a little rake there so you can smooth out the sand ahead of time. And it turns out no matter what angle you shoot from, the holes you make in the sand are round. You cannot produce an elliptical crater. So how'd this get resolved? So let's take a break right here.